Okay. Uh, so up to previous lecture, we have completed construction, working, and mode of excitation for different type of stepper motor. So we have discussed three types of stepper motor in detail. That is variable reluctance stepper motor with a multi-stack and single stack design. Next, second type is permanent magnet stepper motor, and third one is hybrid stepper motor. So we have completed that construction features and application of stepper motor, that much part up to previous lecture. Now, in this particular lecture, we are going to discuss characteristics of stepper motor, that is static characteristics and dynamic characteristics. Before moving towards actual static and dynamic characteristics, initially there are certain important terminologies related to stepper motor. So first of all, we are going to discuss that terminologies, and then after we will proceed towards characteristics of stepper motor. So let's start with the different terminologies. Okay. So first term is a step angle. So this term we have already discussed this particular term in single stack variable reluctance stepper motor. So now step angle is what? The step angle is the angular displacement of a stepper motor or of a rotor of stepper motor when we apply a single pulse of excitation for stator winding. Okay. That means after application of a single pulse of excitation to any one of the phase of stator winding, by how much degree or by how much uh, by how much angle that rotor of stepper motor will displace from its initial equilibrium position, that angle is generally termed as a step angle. So we define the step angle as it is an angular displacement of rotor for a single pulse of excitation which is applied to stator winding. We generally calculate this step angle with formula theta s is equal to 360 degree divided by small n into nr, where theta s is the step angle in degree, n small n is the number of phases, and nr is the number of rotor teeth. Okay. So we calculate step angle with this particular formula, that is theta s is equal to 360 degree divided by small n into nr. Now this formula is applicable only for variable reluctance stepper motor and permanent magnet stepper motor. For hybrid stepper motor, as we have already discussed, there are two rotor stacks. Okay. So as there are two rotor stacks present, therefore, for hybrid stepper motor, we determine this step angle by formula theta s is equal to 360 degree divided by 2 times n into nr. So for hybrid stepper motor, this formula is applicable, 360 degree divided by 2n into nr, where n is the number of phases and nr is the number of rotor teeth, because for hybrid stepper motor there are two rotor stacks. One rotor stack is houses or embedded on a north pole of a permanent magnet which is present on rotor shaft. Another rotor stack is present on a south pole of permanent magnet on which is present on rotor shaft. Okay. So due to that two rotor stacks, there is a different formula applicable to calculate step angle for hybrid stepper motor. Okay. So this is related to step angle. So what is step angle? It is the angular displacement of rotor for a single pulse of excitation which is applied to stator winding. Now next terminology or next definition related to stepper motor is resolution. So what is resolution? Resolution is defined as it is the number of steps per revolution. Okay. So the number of steps completed or number of steps carried out by stepper motor in one particular revolution, that number of steps are generally termed as a resolution of stepper motor. So we calculate this resolution by 360 degree divided by theta s. So when we divide step angle with a 360 degree, then sorry, when we divide 360 degree by a step angle, then that number is the resolution for a given stepper motor. So we define this resolution as it is the number of steps per revolution. The number of steps per revolution is generally termed as a resolution of stepper motor. Now, next, third terminology or definition is a stepping rate. So, what is stepping rate? So, stepping rate is also known as a stepping frequency. Okay. So, the number of steps completed per second is generally termed as a stepping rate or a stepping frequency. So, the total number of steps completed by rotor of stepper motor in one particular second, this number is generally termed as a stepping rate, or that is also termed as a stepping frequency. Okay, so it is the number of steps completed per second. Next, fourth and fifth definition is related to actual positions of that stepper motor or rotor of stepper motor. So there are two different positions. One is the hold position, another one is the detent position. Now, what is meaning of hold position? Now, before moving towards these definitions for position, you are, I think all of you are familiar that there will be two positions for stepper motor. One position when a rotor is, stator winding is excited, and another position is when a stator winding is unexcited. Okay, so during unexcited condition, due to detent torque which is present inside the motor, the rotor of a stepper motor achieve one position, or the rotor of stepper motor remains stationary at one particular position due to the force of attraction between the stator pole and a rotor pole, or stator pole and rotor teeth. So this is actually related to detent torque. Okay, so there are two different positions which are based upon the whether stepper motor is excited or unexcited. So the first position is hold position. So how we define this hold position? So hold position generally corresponds to the resting position of rotor of excited motor. That means when we excite stator of stepper motor, then whatever resting position of that rotor is there during this excitation phase, that resting position is generally termed as a hold position of stepper motor. Now, this resting position generally depends upon the type of excitation. Okay, whether that excitation is single mode of excitation, double mode of excitation, or double phase excitation, or any other type of excitation. So based on that type of excitation, there will be hold position corresponds to rotor. So we define this hold position, or this hold position is nothing but it is a simple position corresponds to the resting of a rotor of excited stepper motor, or when stator winding of that motor is under excitation condition. Reverse to this hold position, there is a detent position. So what is detent position? So detent position generally corresponds to the position of rotor when the stator winding of that particular motor is unexcited. That means when we disconnect stator winding from supply, and whatever rest position of that rotor is there during such unexcited condition, this position is generally termed as a detent position of a stepper motor. Okay, so hold position corresponds to excited stator, and detent position corresponds to unexcited motor or unexcited stator. Okay. Now, next term is important, which is the stepping error. Now, what is the stepping error? So, stepper motor generally made up of some magnetic materials and other materials. So, there is a certain tolerances developed in this manufacturing processes, and due to the properties of these different magnetic materials and the other materials which are used for construction of stepper motor. And due to this particular tolerance, whatever actual step angle of that stepper motor is there, that step angle varies from its theoretical step angle. We generally determine that theoretical step angle with formula theta s is equal to 360 degree divided by n into nr, or it can be determined by 360 degree divided by 2n into nr. So whatever this theta s is there, that theta s is generally theoretical step angle which is calculated for stepper motor. And due to the tolerances which are happen during manufacturing process, and due to the magnetic material and other constructional material, the actual step angle of that particular rotor is not equal to this theoretical step angle. So there is a certain difference exists between actual step angle and theoretical step angle. So the percentage stepping error is given by the percentage stepping error is equal to actual step angle of a motor minus theoretical step angle divided by theoretical step angle. So we generally calculate this percentage stepping error similar to the percentage limiting error or percentage relative limiting error as similar to measurement process. Okay, in measurement process we have seen that terminology, that is limiting error and percentage limiting error. Okay, similarly we can calculate a stepping error. So it is a simple stepping error is the difference between actual step angle minus theoretical step angle. Actual step angle is the angle by which the rotor of a motor displaces from its equilibrium position when we apply the pulse to stator winding. Okay, and what is theoretical step angle? It is the calculated value of step angle, but always there is a certain difference exists between this actual step angle and theoretical step angle, and that difference is generally termed as a stepping error. And we calculate percentage stepping error as actual step angle minus theoretical step angle divided by theoretical step angle into 100. Okay. Now, next term is the positional error. Okay, now what is means of positional error? The maximum range of cumulative percentage error taken over a complete revolution of a rotor is known as the positional error. So initially we have seen stepping error. Okay, now what is positional error? Stepping error is what? Stepping error is the difference between actual step angle and calculated or theoretical step angle. Now what is positional error? It is the maximum range of cumulative percentage stepping error which is taking place over a complete revolution of a rotor. That error is generally termed as a positional error. That means after one complete revolution of a rotor, whatever error which is taking place in this step angle or whatever total error which is taking place in this stepping angle, that particular error is generally termed as a positional error. Okay. Next term is the holding torque. Now what is holding torque? Holding torque is the maximum torque that can be applied to an excited motor without slipping the rotor from the equilibrium position. Okay. So it is simple torque which is applied to rotor of excited motor without slipping of rotor from its equilibrium position. So that torque is generally termed as a holding torque. Now what is meaning of slipping of rotor from equilibrium position? If we apply torque above holding torque, then definitely the rotor will move from its equilibrium position in one particular direction, either in clockwise, either in counterclockwise, which depends upon the direction of applied torque. So the maximum permissible torque which can be applied to such excited motor without slipping of this rotor from its equilibrium, that torque is generally termed as a holding torque of a stepper motor. Okay. Now detent torque, we have discussed this detent torque in permanent magnet stepper motor. So detent torque is what? It is the maximum torque that can be applied to an unexcited motor without slipping of rotor from its equilibrium position. Now this torque is only present in PM and hybrid motor. As we have already seen, a detent torque is only there for hybrid motor and permanent magnet motor because the rotor of this hybrid and permanent magnet motor consists permanent magnets on it, and due to presence of that permanent magnet, there is a magnetic interlocking takes place between rotor teeth and stator pole whenever the motor is under unexcited condition. That means whenever there is any pulse applied to stator winding, under that condition also there is the magnetic locking between stator and rotor teeth takes place due to this permanent magnet. And whatever torque which is required to overcome this force of attraction or whatever torque which is required to overcome this magnetic locking between rotor and stator, that particular torque is generally termed as a detent torque for a stepper motor. Okay. Now, depending upon the mode of excitation, there are two different operating modes. One is the start-stop mode and second one is the slewing mode. Now, what is meaning of this start-stop mode of stepper motor and what is meaning of a slewing mode of stepper motor? Okay. So, what is start-stop mode? So, start-stop mode is a mode of operation of stepper motor in which a second pulse is applied to motor only after rotor attains its steady position due to first pulse. So initially, suppose we apply first pulse to the stepper motor, and due to that first pulse applied to the stator, the motor will rotate in a one particular direction with a certain step angle. That step angle depends upon the mode of excitation. Okay, so either that motor will rotate with a full step angle or maybe with a half step angle, which depends upon the excitation which is applied to that particular mode. Now, if we apply second pulse after the rotor has attained the steady state or rest position or due to first pulse, then such mode of operation is generally known as a start-stop mode of operation. So generally, the single phase mode of operations are generally belongs to start-stop mode of operation, because in single phase mode or single pulse mode, we generally apply a second pulse after the motor attains a steady position due to the first pulse. Okay, so we generally initially apply first pulse. Due to that first pulse, rotor will rotate in some direction with some step angle. Once that rotor attains its rest position or equilibrium position, after that we apply second pulse. So such type of modes, a mode of operation is generally known as a start-stop mode of operation. Now there is a second mode of operation which is the slewing mode of operation. Now what is meaning of this slewing mode? So in this mode there is a opposite operation than that of start-stop mode. So in slewing mode of operation, the second pulse is applied before motor has attained the steady position due to first pulse. Okay, so initially we apply first pulse, but before rotor attains its steady position or rest position, we generally apply second pulse. After that we apply third pulse and so on. So this such type of mode of operation is generally known as slewing mode of operation. And in this slewing mode of operation, there is a continuous excitation pulse exists for stator winding. Therefore, motor cannot be stopped immediately by stopping the applied pulses. Okay. Also, the motor cannot be started in this particular mode. So whenever we have to start stepper motor, we have to go with a start-stop mode only. So initially we have to start that motor with start-stop mode, and then after we can switch that motor in slewing mode. Okay. So in slewing mode, the pulses are generally applied in continuous manner till we are not going to wait till the rotor attains its steady state position after first pulse. So before that rotor comes to its initial steady state, after application of first pulse, we apply second pulse directly. Okay, so that rotor does not attains its state rest condition, or you can say that steady state condition in slewing mode of operation. Now next term is the pull-in torque. Now what is pull-in torque? So pull-in torque generally corresponds to the maximum torque developed by stepper motor for given stepping rate in start-stop mode of operation. So pull-in torque is generally observed in start-stop mode of operation, and it is defined as it is the maximum torque developed by stepper motor for the given stepping rate. Now I think you are familiar with this stepping rate or stepping frequency. So the torque, maximum torque which is developed by stepper motor for the given stepping rate in start-stop mode of operation is generally termed as a pull-in torque. Reverse to this pull-in torque, or the parallel definition to this pull-in torque, is pull-out torque. So what is pull-out torque? So pull-out torque is generally observed in slewing mode of operation. So pull-out torque is the maximum torque developed by stepper motor for giving stepping rate in a slewing mode of operation. So that torque is generally known as a pull-out torque. Now, depending upon the pull-in torque and pull-out torque, there are pull-in range and pull-out range. Okay, so what is meaning of pull-in range? So pull-in range is the maximum stepping rate at which the stepper motor can operate in start-stop mode, developing a specific torque. Okay, so in pulling range, it is the maximum stepping rate at which the stepper motor can operate in start-stop mode by developing a specified torque. So that particular range of operation is generally termed as a pull-in range. Same type of range is there for pull-out torque, that is pull-out range. So pull-out range corresponds to the maximum stepping rate at which the stepper motor can operate in slewing mode, developing the given torque. So pull-out range is generally for start-stop mode of operation. Sorry, pull-in range is generally for start-stop mode of operation, and pull-out range is generally for slewing mode of operation. Okay. So these are the pull-in range and pull-out range. Now next, pull-in rate and pull-out rate. So what is means of pull-in rate? So pull-in rate is the maximum stepping rate at which stepper motor will start or stop without losing synchronism against the given load torque. Okay, so that is pull-in rate is for start-stop mode. So for start-stop mode, there are three different terminologies. One is the pull-in torque, second one is the pull-in range, and third one is the pull-in rate. So what is pull-in rate? It is the maximum stepping rate. Stepping rate is what? Number of revolutions per second. So it is the maximum stepping rate at which stepper motor will start or stop without losing synchronism against the given load torque. And pull-out rate is what? It is the pull-out rate corresponds to the maximum stepping rate at which stepper motor will slew. Okay, so that rate is generally known as a pull-out rate. Okay. Now next important terminology is the synchronism. So in previous certain terminologies, you have heard synchronism. So what is this synchronism for a stepper motor? So synchronism means one-to-one correspondence between the number of pulses applied to stator and the number of steps through which rotor has actually moved. Okay, so it is a simple correspondence, one-to-one correspondence between stator and rotor. So in what condition we will say stepper motor is under synchronism? If that motor rotates, or if the rotor rotates with the desired step angle after application of each excitation pulse to stator phase, then that motor is said to be in synchronism. That means, say the step angle for the motor is 15 degree. We apply mode of excitation in such a way that motor rotates in 15 degree in, say, clockwise direction after each pulse. So say we apply first pulse to stator, motor will rotate in 15 degree in clockwise direction. If we apply second pulse to stator, motor should run with next 15 degree, third pulse next 15 degree, and so on. So after application of each excitation pulse to stator phases, motor should run by its desired step angle for each pulse. So if such operation is there, then we can say that stepper motor is under synchronism. If there is a certain misbehavior between this excitation pulse and the rotor rotation, then definitely motor is under out of synchronism. Okay, sometimes might be motor runs with half of step angle, or sometimes a motor refuses to rotate after application of a pulse to a particular stator phase. So under that case, we can say that motor is under out of synchronism. Okay. So for each and every pulse of excitation or excitation pulse to stator, motor should run with its desired step angle in desired direction. And if such thing is there for a stepper motor, then we say that stepper motor is under synchronism. Otherwise, that motor is out of synchronism. Now, next terminology, these are not so important, okay, but let me discuss mid-frequency resonance. So at certain input pulse frequencies, the motor torque droops at to a lower value, and this particular phenomenon is generally termed as a mid-frequency resonance. So for a certain input pulse frequencies, the motor torque droops from its desired value to lower value, and that particular frequency is generally termed as a mid-frequency resonance. Next one is there is a terminology related to slew range. So slew range is the range of a switching rate between pull in and pull out with which the motor runs in synchronism but cannot start up or reverse. Okay, so these terms are not so important. So up to synchronism, that much terms are important. Then there are three remaining terms. You can go through these particular terminologies. That is response range, start-stop stepping rate, and ramping. Okay, so that terms are not so important for a stepper motor. Okay, but I'm going to provide this PDF on Google Classroom. You can go through that terms also. Now, these are the various terminologies related to stepper motor. Maybe in next lecture, we are going to discuss one or two numericals for calculation of resolution and stepping rate for stepper motor. So for that numericals, some of the terminologies from this from these terms are very important. Okay, therefore we have discussed these particular terminologies. Now let's move towards the actual characteristics of stepper motor. So there are two different characteristics of stepper motor. One is the static characteristics of stepper motor, and second one is the dynamic characteristics of stepper motor. So when we plot torque versus step angle, when we plot torque T versus step angle theta S, then these characteristics is generally termed as a static characteristics of stepper motor. Similarly, if we plot torque versus current characteristics, this current is actually excitation current. So torque versus excitation characteristics, that characteristics is also a static characteristics of a stepper motor. Now, how to plot these static characteristics for stepper motor? So, whenever we have to plot static characteristics of stepper motor, first we brought that stepper motor to equilibrium position. So, to brought that stepper motor to equilibrium position, initially we have to excite one of the stator phase of stepper motor by external excitation pulse. Once we excite that particular phase of stepper motor, then the rotor teeth came in magnetical locking with that stator phase, and this position is generally termed as a equilibrium position of stepper motor. Now, after broughting that motor, or after once we brought that motor to equilibrium position, then we have to apply, or then we have to vary the external torque. Okay, then we apply external torque to that motor. Now this make rotor moves from its rest position. So when we apply external torque, motor will move from its initial rest position. So by varying this load torque, we have to simply measure the angular displacement of a rotor from its equilibrium position. That means simply vary this load torque, and for that corresponding load torque, measure angular displacement of rotor. After measuring the torque versus theta s, we have to plot this torque versus theta s. So the variation of this displacement with respect to torque gives us a static characteristics of stepper motor, which is also termed as torque angle characteristics of a motor. Okay. And the typical torque angle characteristics of a motor is as shown in figure. So where theta s is what? It is the step angle. Okay, that is nothing but the angular displacement of a rotor corresponds to every load torque variation. Theta m is the maximum step angle. Okay, so as we vary torque, then for initial condition, the value of theta, that is step angle, get varies. After the maximum value, if we still vary the torque value, or if we still vary the theta, that is angular displacement, then there is a fall in torque. Okay, so this will be the typical curve of a torque versus load, torque versus angle, which is also termed as a static characteristics of stepper motor. Similarly, we can plot torque versus current characteristics. So this current is actually excitation current. So by simply varying, same procedure we have to follow. That means initially we have to brought that motor to equilibrium position. After that, we have to vary, we have to apply load torque to that motor, and by varying load torque, we have to measure the excitation current. If we plot that torque versus excitation characteristics, then that torque versus excitation curve for typical VR motor and hybrid motor is as shown in figure. Okay. So this particular curve is generally termed as a torque versus current characteristics. That is also known as the static characteristics of stepper motor. Okay. So always keep in mind torque versus step angle and torque versus current, or that is also termed as a torque angle characteristics and torque current characteristics. These two characteristics are generally static characteristics of stepper motor. Now next, move towards the dynamic characteristics of stepper motor. So dynamic characteristics of a stepper motor generally represents the characteristics when motor is under running condition or about to run condition. Okay, so the dynamic characteristics is plotted during running condition of a motor. So pull-in and pull-out torque characteristics are generally called as a dynamic characteristics of a motor. So pull-in torque characteristics and pull-out torque characteristics. So basically these characteristics is plotted between torque and stepping frequency or stepping rate. So stepping frequency or stepping rate is actually number of steps per second. Okay. So the characteristics between torque versus stepping frequency or stepping rate is known as the dynamic characteristics of a motor. So there are two different characteristics. One is the pull-in characteristics, which is corresponds to pull-in torque, and second one is the pull-out characteristics, which is corresponds to pull-out torque. Okay. So this particular curves refers to the range of frictional torque against which the motor can start without losing a step angle. So pull-in characteristics is generally termed as a starting characteristic. So whatever pull-in characteristics we are is shown, which is shown in this particular figure, that characteristics is generally known as a starting characteristics, and this curve is generally refer to the range of frictional torque against which the motor can start without losing step angle. That means this is the initial starting characteristics of motor. The pull-out or slewing characteristics is plotted between the frictional load torque and the maximum pulse rate at which the motor can be synchronized. Okay, so pull-out characteristics is generally plotted between the load torque and maximum pulse rate, or you can say that it is plotted between the load torque and maximum stepping frequency during the synchronism condition. So when motor gets synchronized, under that particular synchronized condition, we plot this pull-out curve or pull-out characteristics of stepper motor. So these pull-in curve and pull-out characteristics, or pull-in torque characteristics and pull-out torque characteristics, are generally dynamic characteristics of stepper motor. Okay. So if you look towards this particular figure, then pull-in torque is OQ. So OQ is actually pull-in torque. So this is the pull-in torque for motor at stepping rate of A. So for a stepping rate of A, or at stepping rate of A, the OQ is the pull-in torque. Pull-out torque is OR. OR is the pull-out torque. Okay, that means this particular torque is your pull out torque for stepping rate of A. Pull-in rate at B for torque OP. So at B, the torque is OP, which is the pull-in torque, and for the corresponding pull-in torque of OP, the stepping rate is B. Okay, that is OB is the stepping rate. Okay, then pull-out rate is C. What is pull-out rate? Pull-out rate is C for torque OP. For OP, the pull-out rate is C. Okay, and response range is OB. So OB is the response range for the stepper motor for the given dynamic characteristics. Okay. So this is about the static and dynamic characteristics of a stepper motor. Now in next lecture, first of all, we will discuss one or two numericals of a step angle and resolution calculation. And after that, we will proceed towards last bit of this chapter, which is control of a stepper motor. So in that, we are going to discuss open loop control of stepper motor, closed loop control of stepper motor, and microprocessor based control, microprocessor or DSP based control of stepper motor. So initially in next lecture, we are going to discuss some numericals based on stepping rate, step angle and resolution, and if possible, we will discuss the control strategies of a stepper motor.